Hi, welcome to the mathcenter.com. In this video, we are going to look at a physics problem in nuclear physics. This question that I am going to talk about appeared in the CIE exams. Okay, the CIE exams, I've made a note here, May-June 2014. This appeared in paper 4, okay, of the physics exam. The subject code 9702/42. Okay, again, the subject code of this physics paper 9702/42. This is question number 9. The question that we're going to talk about is question number 9 for a total of 10 points. And again, let me remind you, it's a CIE exam paper, May-June 2014. Okay, good. You can download the question paper from the website. So I have paraphrased the question on the board here so that it's easy for us to talk about it. Okay, it's got a few parts to this question. This question has got a few parts. We're going to go slowly bit by bit. Let me take you through it. Yeah? Again, let me remind you, it's a question that is based on nuclear physics, yeah? The nuclear physics portion of our syllabus. Okay. As you must do in physics all the time, make sure that you read the question very carefully and then you can attack it. Okay? Some water becomes contaminated with radioactive iodine 131. Okay, so you've got some water, it gets contaminated with radioactive iodine 131. Now the activity of iodine 131 in 1 kg of this water, okay, the activity of iodine 131 in 1 kilogram of this water. Okay, so let me just, this is activity of iodine 131 in 1 kg, yeah, 1 kilogram of this water is 460 becquerel. Okay, you're also told that the half-life of iodine 131 is 8.1 days. So I've scribbled in some notation here. Okay, some books like to write it as a little t with a 102 as a subscript. Sometimes they like to use as, you know, a capital T with a 102 as a subscript. Okay, good. Let's start with the question. Define radioactive half-life. So I'll make some remarks here. Half-life definition, you can easily pick it up from any standard physics textbook. Okay, so let's start with, I'm going to give you a small or rather a short explanation before I talk about the definition. Okay, so let's start with some radioactive nuclide. Okay, and N0 here is the number of undecayed nuclei. Okay, that's the initial number of nuclei that we have. That's why we like to call it N0. Okay, this is not no, this is N0. Okay, so number of undecayed nuclei, the time that it takes. Okay, this is a half N0. Now the time that it takes, that's why I've written it in red here, for the number of undecayed nuclei to be reduced to half its original value. Okay, the time that it takes, okay, for the number of undecayed nuclei to be reduced to half its original value. So you start with N0, you end up with a half N0. The time that it takes, because radioactivity, okay, is, you know, a random process, so the time that it takes to get from here to here, this is called your half-life. So write out a proper coherent definition. You'll find it in standard textbooks. I like to use this, okay, the time taken for the number of undecayed nuclei to be reduced to half its original value. Okay, and we're done with that part. Okay, next part of the problem. We're asked to calculate, okay, I know the writing here is horrible, but look up the question on the question paper itself. Calculate the number of iodine 131 atoms. Again, calculate the number of iodine 131 atoms in 1 kilogram, okay, in 1 kilogram of this water. Okay, so let's start slowly. Let me remind you, we're trying to find the number of iodine 131 atoms in 1 kg of this water. What is the activity of this 1 kg of this water? You are told the activity is 460 becquerel. So these are the numbers we need to keep in mind. Okay. First off, we are given our half-life is 8.1 days. Okay, 8.1 days, and we know that let's do a bit of work here. Our half-life, we know by formula, is ln 2 over lambda. Okay, half-life is given. This formula we know, half-life is ln 2 over lambda. So we can work out lambda, okay, the decay constant. Lambda is a decay constant, as ln 2 over our half-life. So some of you may want to write this formula straight away. Feel free to do so. Okay. So now let's work it out. I have ln 2. My half-life is 8.1 days. How many hours in a day? 24 hours in a day. How many seconds in an hour? 3600. So now we can write down lambda. I worked it out. Let me write it down for you. Okay, I worked it out. And the value is 9.9 times 10 to the power of -7. Okay, that's the value of lambda. Okay, halfway there, we are asked to work out the number of iodine atoms in this 1 kg of 1 kilogram of water. So let's use the famous formula. Okay, A equals to lambda n. Okay, what is A? Your activity. Okay, your decay constant and your number of atoms. Okay, activity. Do we know this? Yes. 460. Lambda, we know. Do we know this? Yes. We just worked it. What are we trying to find? N. And we are done. So let's plug in the numbers. If you need to know what this formula means and so on, you can get in touch with the method.com and I'll come back to you. Okay? But this, we're just trying to solve a problem. Use the formula that is found in your tags, in your notes, and so on. Okay? So I have 460. And lambda is 9.9 times 10 to the power of -7. Use a calculator. And you will get, let me write down the answer that I worked out. You will get n equals to 4.64 times 10 to the power of 8. So let's just take it as 4.6 times 10 to the power of 8. And we are done. Okay. The next part of this question, an amount of 1 mole of water has a mass of 18 grams. This is something that we would have seen in our O-level chemistry. But anyway, this question, the information is given to us. An amount of 1 mole of water has a mass of 18 grams. You're asked to calculate a ratio. What's the ratio? The number of molecules of water in 1 kilogram of water. Again, the numerator of this ratio, the number of molecules of water in 1 kilogram of water, and the denominator is number of atoms of iodine 131 in 1 kilogram of contaminated water. Okay, so it's number of molecules of water in 1 kg of water over number of atoms of iodine 131 in 1 kg of contaminated water. Now this ratio, the numerator we know, number of atoms of iodine 131 in 1 kg of contaminated water we know. We just worked in the earlier part. So let's write that down. Oops, excuse me. 4.6 times 10 to the power of 8. We worked that out earlier. All we need is the number of molecules of water in 1 kg of water. Now, so let's do a little bit of working here. 18 gram of water, that's 1 mole, right? 18 gram of water has 6.02 times 10 to the power of 23 molecules. Okay, so we are talking about 1 kilogram. So 1 kilogram of water is how many? So we know it is 6.02 times 10 to the power of 23, and 1 divided by 18 gram will be, in kilogram will be, times 10 to the power of minus 3. Okay, so when you work this out, use a calculator, and that number will come out as 3.34 times 10 to the power of 25. Use a calculator and you'll get your final answer, 7.26 times 10 to the power of 16, or just 7.3 times. Okay, 7.3 times 10 to the power of 16, and we are done. The last part C of this question. Let's read it. An acceptable limit, excuse me, an acceptable limit for the activity of iodine 131 has been set out as 170 becquerel per kilogram. Okay, and acceptable limit for the activity of iodine 131 has been set at 170. Okay, 170 becquerel per kilogram. That's the acceptable limit. You asked to calculate the time in days. Okay, you asked to calculate the time in days for the activity of the contaminated water to be reduced to this acceptable level. Okay, got it? You asked to calculate the time in days, careful, time in days, for the activity of the contaminated water to be reduced to this acceptable level. Where did we start? We started at 460. Now remember, the acceptable limit is 170. So we know the formula we're going to use. Let's start with A equals to, let's use the formula, the activity formula, E minus lambda T. Okay? A equals to A naught, E to the power minus lambda T. Lambda, okay, this is from the formula T1 over 2 equals to ln 2 over lambda. Therefore, lambda will be ln 2 over, okay, so this will be ln 2 over, we are given, okay, the half-life we are given in this problem is 8.1 days. Okay, now let's just plug in the rest. We're looking at acceptable limit is 170, so let's plug in 170. We started with 460, E is about minus. We are done basically, yeah. So we have an equation, one unknown, we can solve it, and we're done. So we have E is about minus ln 2 over 8.1 T equals to 170 over 460. Take logs, okay. Okay, take logs to both sides. You'll get minus ln 2 over 8.1 T equals to ln 170 over 460. Use a calculator and you solve, you'll get T equals to 11.6 days. Okay, and we're done.